Hi, my name is Philip, and I'll be presenting our work on a recommender system for tracking vulnerabilities. This problem was observed in our research to automate the vulnerability analysis problem, and that problem exists because entities are flooded with several vulnerabilities on a recurring basis, and they need to identify those, triage those, and be able to manage the work associated with those limited resources. And so there are a lot of AI solutions that can assist with this problem. But when field testing solutions, we ended up spending several days on this annoying naming problem because on one hand, entities have software and hardware inventories that are available through spreadsheets, APIs, various other means. But then the public vulnerability repositories, such as the National Vulnerability Database, have standard naming conventions. And surprisingly, there's very little correlation between what's reported through the inventory system and the NVD and repositories such as the NVT. Now, there are a few vendors who play nice and present the package of vulnerabilities that need to be addressed based on artifacts within the system. But most entities have hundreds to even thousands of vendors that they contend with, and they have to match all of these to understand what vulnerabilities their systems may have. And any of these vulnerabilities may allow an adversary to gain access. So it's not enough just to focus on the major companies that regularly and report and play nicely with the matching. It's the entities have to deal with all vendors that supply their software. And so as a result, in the best case, entities may spend the time to do this, and they spend numerous hours tracking vulnerability sources and producing these comprehensive vulnerability and patchwork packages. But more commonly, the vulnerabilities just simply remain unidentified because the resources don't exist to receive those notifications. And perhaps this was less of a problem when only a handful of vendors publicly reported their vulnerabilities, such as many of you may remember that there was a time where really only Microsoft reported on a regular basis, and you had this Patch Tuesday window. And now you have several vendors that are reporting on a regular basis. So you have a number of companies, and bug bounty programs have become more popular and are reporting more vulnerabilities. And you also have government agencies and even smaller companies now that this is becoming more commonplace to report the vulnerabilities. So one possible option that we naively assumed is that you could apply this great matching database between what is reported by these systems and what the public vulnerability repositories have listed. But this is problematic because there are so many legal and regulatory issues with sharing the inventory information. Entities have a problem because just the presence of software in their environment or hardware in their environment could save an adversary months of reconnaissance activities in performing a targeted cyber attack against the entity. And so this data is very sensitive. And for software vendors, they often don't share this mapping information for artifacts that they have in their software because maybe the data is considered proprietary, but more often they simply don't have the resources to maintain this and publish this for public consumption. So after repeatedly performing this task, we observed a common process of tying the asset inventory to public vulnerability repositories. And this inspired us to consider how wonderful it would be if we could simply automate this process and save a few days in field testing as a result. That's the selfish reason. Now, for entities, this is more of a survival need to be able to associate these and gain better information about the vulnerabilities that are coming out on a day-to-day basis. So we produced a recommender system for the common platform enumerators. And this is like any other recommender system that you might experience many times a day through your web query, social media application, where you're honing in on a result and there's just too much noise to produce a deterministic outcome. And so this recommender system provides not a perfect result, but a very likely optimal match to where entities don't have to search for, or they can automate this the searching process to identify the appropriate match. So let me take a step back and describe some of the background on the common platform enumerator. This is a standard from the United States National Institute of Standards and Technology that is used by the National Vulnerability Database, among other repositories, to associate vulnerabilities with named software. And this works in practice with the NVD through a consortium of CVE naming authority, common vulnerabilities and exposures, CVE naming authorities. They will, they're represented by these large software producers, and they will, when reporting vulnerabilities, this is how they associate which products are indeed vulnerable. So you have major software producers, service CNAs, but you also have bug bounty programs, vulnerability researchers, national agencies, incident response teams. They will all, anybody who is reporting vulnerabilities may be producing these common platform enumerators. The common platform enumerator is a URI, and which represents more granularly from left to right. So it's a search string in the URI form. And it provides the flexibility to search very broadly and then lock in on a desired targeted CPE. And the CPE, although it may go down 10 or more levels of granularity, we found that for identifying vulnerabilities, it's really only useful to go down to the product level. And the recommended strategy is to keep the target CPE at the highest level possible. This reduces the possibility of having false negatives where the entity has the risk of missing a vulnerability notification. So one strategy might be to only include the vendors, but in many cases, this floods the entity with several false positives. For example, it may be safe to identify a target CPE at the vendor level when the vendor only has one or two products. Now keep in mind, the CPE dictionary is not comprehensive, and so vendors don't usually provide CPEs for products where vulnerability has not been reported. So if a vendor only has one or two vulnerabilities a year, then even if they don't have the products identified, you can still safely track vulnerabilities without the fear of missing one. Then if the product's not identified now and there's a new vulnerability for it, then it will still show up based on that vendor match. But for a vendor like Cisco or Google or Microsoft that has tens of thousands of products and then also report tens of thousands of vulnerabilities each year, it would be overwhelming to track that at the vendor level, like track all vulnerabilities reported by Cisco. And so this leads to our approach for automating the CPE matching problem. We basically take the approach that an analyst would take in identifying these matches. An analyst would sit down, and we have two examples here on the extreme sides of product types. So on the first example, you have a Cisco Catalyst 1200. The analyst performs the search and finds their desires to find a closely matching CPE. Now, if they decide to match at the vendor level, as we've already talked about, we would have these silly reports where the Cisco Catalyst 1200 has new vulnerabilities that are associated with something like Cisco WebEx. So instead, we have to go down to the product level. And this is also a little confusing because there's not a perfect match. Instead, the analyst is going to observe that the past vulnerabilities for the Catalyst 1200 are associated with the CPE for Catalyst 12XX. supervisor software. And at this point, they could go further and specify the version, but this often changes. So we decide to simply take the trade-off of having less maintenance for a little less perfection in the matching CPE. Now, on the other extreme, you have this PuTTY software. PuTTY is an SSH tool, SSH client tool that's commonly used on Windows workstations. And it turns out the open source PuTTY vulnerabilities are associated with its creator, Simon Totham, not the vulnerabilities themselves, but the CVEs. The vendor is Simon Totham. But Simon Totham only has this single product listed, and there are only 3 vulnerabilities a year on average. So we have the safe option of associating any vulnerability from Simon Totham products to our PuTTY software in the inventory. And so that's the approach that we're trying to mimic with the recommender system. So now getting into the automation. We want to simulate the simple search, taking into account the hazards of human error and the search on both the vendor and the product. So the CPE standards is guaranteed to have both the vendor and product fields, but asset inventories are more haphazard. So we need to account for several problems in the matching. We may have missing vendors. Inventories could have spelling errors, even installations can have spelling errors, and then the vendor and product name may change. So to address these, we extract out the candidate CPEs using both the natural language processing word vector cosign similarity and the more simple character cosign similarity. The more simple similarity measures how similar the characters in one word are to the target word. But the simple measure doesn't capture the possibility of, say, company or product name changes. And on the flip side, word vector similarity can handle product name changes, but they have a difficult time with handling out of vocabulary words or words which the NLP model has not been trained on. Now, we take the similarity measures, but the similarity measures alone are not enough to determine quality recommendations. The analyst would look at several data features to determine a good target CPE, as we already went through. Our automation does this by extracting the data features of similarity, but also information about the number of products, the frequency of vulnerability reporting, and even the CVE naming authority itself. And then the model has 2 outputs. The first output determines whether the recommendation should match at the vendor or product level. And then the second output, a more interesting output, is the order in which to present back the CPE match from highest to lowest, or even reject. So to build the model, we couldn't use the products that we've identified in field testing. So we scraped Wikipedia software and hardware product categories and extracted over 23,000 samples by which we would then identify and try to match up to the to a CPE. We use a random forest classifier over a decision tree classifier, and that's for just better performance and to reduce variance in the model, especially with that many training samples. We use an 80-20 train test split, 80%, 20%, and the model results for the recommendation order classification are presented here. We also have output for the CPE match granularity, vendor and product, but those results are less interesting because really the output is primarily split based on the number of vulnerabilities that a vendor reports. So for the order classification, we have very high F scores for the extreme cases. And this is because it's easier to consistently classify the highest recommendations. We simply look at high similarity scores between vendor and product, and then low and reject scores are on the other end. We simply look for these low similarity scores and then classify those as low or simply just reject. Don't even present these back to the user. The middle order classifications require a little more judgment, but we suspect the smaller number of samples, this is compensated by a human analysis, and because they're able to digest the smaller number of samples presented back to them. In our implementation results, we looked at 50 software products and 50 hardware products, and had an analyst go through and identify those. The biggest result was the 7 hours spent by the analyst to identify those recommendations were reduced to the immediate analysis of the recommender system. And we see improvement both in the number of results presented back to the user, significant reduction in the number of results, and then also the percentage of results that were conclusive. It's important to point out that several products are not represented with the CPE, and it's much more difficult to validate the absence of a CPE. So we considered no results to be inconclusive for this study. In conclusion, we've improved the process for associating public vulnerability data features to an entity's asset inventory, and we do so by mimicking the human analyst process of identifying an optimal target for target CPE for software and hardware. This approach goes beyond fuzzy matching to identify a match which considers the dangers of false negatives. It minimizes the number of false positives, and this approach has proven useful for reducing the time requirements and improving the accuracy in producing these CPE mappings. Thank you.